Thank you, Alan. So now we have our last talk of this first Ithaca meeting of 2024. And we are glad to have Alan Cigoli from University of Torino that we talk about from Yoneda's additive irregular spans to fibred cartesian monoidal opfibrations. Please, Alan, it's your time. Alan, we don't hear you because your mic is off. Okay.
Okay.
Thank you.
Sorry. Thank you, Beppe, and thank you for this invitation. And let me first apologize with the previous speakers. I was not able to participate because we had a meeting in the department, so I was only able to come at 4. And many thanks to Manuel, who accepted to speak before me. Okay, so what I'm going to talk about is something I already talked in Louvain-la-Neuve 2 months ago. Probably today I will be able to go a bit further. I hope I will be able to go a bit further. And what I will talk about is somehow a summary of works that I did together with Sandra Mantovani, Beppe Metre, and Enrico Vitale in the last, say, 4 or 5 years about a study of an intrinsic definition of cohomology. Let me start with the Yoneda and extant groups defined by Yoneda in this famous article. Okay, let us assume A is an abelian category. An exact sequence or length, I would say 2, but it depends on what you take as a reference. I take these middle objects, so this is for me a sequence of length 2. It's just an exact sequence in our abelian category. We've got morphisms of such sequences in the obvious way. Those are 4 tuples of morphism such that those 3 square commute. There's a category of extensions on length 2, which I will denote with x to 2. And we've got an obvious functor from this category projecting to the rightmost and leftmost components. I will call S this functor, which is in fact given by a pair, S0, S1. And we will denote by X2AB the fiber over a pair AB of objects in our abelian category. So the elements of the classical group X2AB are nothing but the connected components of this category. So are connected components of sequences of length. Now, if we fix an extension E from B to A, and a morphism from A prime to A, in an obvious way, we can lift this morphism alpha to a morphism of extensions in such a way that the beginning object is always B. And this morphism as an obvious universal property because it is constructed via pullback, so it is universal among all morphisms of extensions whose rightmost component factors through alpha. In other words, the functor S0 projecting to this rightmost component is vibration of categories. And we can choose liftings in such a way that when we take the leftmost component, we get an identity. Okay, dually, if we take a morphism beta from B to B prime, we can construct via push out lifting of this beta, which is in fact an op-Cartesian lifting, and then S1 becomes an opfibration, where we can choose liftings to be the identity on the rightmost component. So what Yoneda did was isolating the formal properties of this category of sequences, and he defined what is called a regular span, which is just a span of functors where S0 is a fibration with S1 vertical Cartesian liftings, and S1 is an opfibration with S0 vertical op-Cartesian lifting. What Yoneda proved, not in the way I describe it here, but essentially that's what he proved, is that every span admits a factorization through a regular span whose fibers are discrete. So if we fix A and B, the fiber SAB is a set, essentially. Okay, so this functor S bar, which has discrete fibers. As a consequence, we get a functor, it is defined a functor, S bar minus 1 from A op times B to set. There are subtleties in here, but I don't want to go into details. And the elements of this of S bar minus 1 AB are precisely the connected components of the fiber of S over the same pair AB. Now, if S is not just a functor, but an additive functor, so X, A, and B are additive categories, and this is additive, then this S bar minus 1 preserves products in each variable. And hence, for each pair of objects AB, the set S bar minus 1 AB inherits an abelian group structure. And that's what Yoneda proves. Now, if we go back to the case of extensions, the above procedure precisely gives a way to endow the X2AB with a group structure. And this group structure is the so-called bare sum. Here is a concrete construction, but maybe it's better if I skip this. Okay. Now, if we move to non-abelian context and consider, for example, group cohomology, it is well known that group cohomology can be interpreted again in terms of crossed extensions. In terms of extensions, but not as in the abelian case. We need to consider crossed extensions. What are these? Well, the crossed extension is again an exact sequence of this kind where G is a group, E2, E1 are groups, and B is an abelian group. But the middle arrow needs to be, in fact, a cross module. And morphism of such are 4 tuples, such that, of course, the squares commute, but the middle square has to be a cross module morphism. Okay. With a node by X to the category of crossed extensions on length 2. And as in the abelian case, we have again that pullbacks provide Cartesian lifts. But so the functor P0 that sends any such extension to its rightmost component is a fibration. But here the symmetry is broken because push-outs no longer provide op-Cartesian liftings. In fact, to have op-Cartesian liftings, one has to consider the G module structure on B. In fact, any crossed extension, go back here, when you have a crossed extension, there is an action of the group G on the abelian group B, which gives a G module structure. And we can only construct op Cartesian liftings along G-module morphisms. So if beta is not just a morphism of abelian groups, but a G-module morphism, then we can construct by a procedure called push forward a lifting of beta to a morphism of crossed extensions. And this construction explains that, in fact, this lifting is universal, and this construction explains that the functor that takes all crossed extensions of length 2 ending in G to G modules is an opfibration. In fact, it is it is an observation. In fact, we can do this even more in general, not only for groups, but also for semi-abelian categories, and we can do this not only for crossed extensions of length 2, but also for crossed extensions of higher length. But there is a problem, because this situation does not fit into Yoneda's framework. In fact, there is no regular span for crossed extension. So we need to find something that replaces the notion of regular span and can be adapted to this situation. And in fact, there is something. The point is to regard what originally was the span from x2 to a times a as now as a functor from crossed extensions to not just groups times abelian groups, but modules. Instead of taking pairs, we need to take triples. A group G, an abelian group B, and an action of the, the group G on the abelian group B. And moreover, we can see that this functor is a fibred functor, is a morphism of fibrations. In fact, modules give a fibration on groups just by the forgetful functor. And crossed extension, as we have seen before, have a fibration P0 over group. So, isolating the formal properties of this triangle, we introduce the following definition: a morphism of fibrations, as in this triangle, is called fiberwise of fibration if for each object in the base category A, the restriction of P, of this upper functor P, to the fibers over little a is an opfibration. And in fact, we proved that this notion is a generalization of the notion of regular span. That is, a functor S from a category X to product A times B is a regular span if and only if this triangle is a fiberwise of fibration, where we took a 0 and then the first projection of the product. Okay. And again, we get a factorization as in the Yoneda situation. This fiberwise of fibration admits a universal factorization through a fiberwise of fibration P bar, which has discrete fibers. In fact, Yoneda didn't prove the universality of this factorization, but we can show that, we could show that this factorization is universal because, say, in two categorical terms, Q is the co-identifier in the two category of fibrations over A of the identity of P. Okay, now if you go back to crossed extension, in that case, X is the category of crossed extensions of length 2, and X bar can be constructed as in the abelian case by taking as objects the connected components of each fiber of P. So those are connected to components of the category of two crossed extensions with the same initial and terminal object. Those are also called similarity classes. Now, mod is, by mod I mean the category of all G modulus for all groups G. Sorry. This is not an abelian category. So we cannot express additivity of such a functor. But the fibers of the forgetful functor over groups are abelian categories. The category of G modulus for a fixed group G is an abelian category. And each object has an internal abelian group structure. And if we restrict our P bar to the fiber over this group G, we get an opfibration with discrete fibers. And so there is an induced functor that takes any G module to the corresponding fiber, which is set. And again, this functor preserves products. And so for each G module, B phi, the fiber over it has an abelian group structure, just by general by a general argument. Such group is also denoted by opx2 of the module, and the group operation is again the by a sum, which can be defined also in this case. And this group is well known to be isomorphic to the third cohomology group of G with coefficients in the module B phi. So the above procedure provides an intrinsic definition of cohomology groups. And I did it for groups, but it can be done in a semi-abelian context and even more in general. So now there are questions that arise. Okay, with the notion of fiberwise opfibration, we handled the problem of the break of symmetry, but there is also a question about the group structure. So we wanted to understand which properties of the restriction PG induce such a good behavior on this P bar G minus 1. Why this functor preserves products? What's the intrinsic property that gives this? And the second question was, can we have a two-dimensional version of this? That is a different factorization through another fiberwise opfibration we call P tilde, with groupoidal fibers, and such that the fibers of these are symmetric to groups. The idea is that, in fact, these cohomology groups are a shadow of a higher dimensional structure, of cohomology 2 groups. So we wanted to take care of all of this. Yes, a bit more ambitious, but in the end, we got something. Okay, so first of all, let us try to understand why this PG minus 1, P bar G minus 1 sends groups to groups. First of all, of course, we want our functor to send monoids to monoids. And here there's a result which is very useful, a result by Müller-Vasilekopoulou. I wrote here a bit of an interpretation of it, but I think that's good. Let X and B be monoidal categories and P an opfibration from X to B, then the corresponding pseudo functor is equipped with a lax monoidal structure if and only if P is a strict monoidal functor and the tensor product of op-Cartesian liftings is op-Cartesian. Why do we want this? Because we want, well, lax monoidal is what makes a pseudo functor send monoids to monoids, or better, pseudomonoids to pseudomonoids. And if this is the case, we call P a monoidal opfibration. Well, they called P a monoidal opfibration, and F a monoidal op-index category. And this condition guarantees that f, this functor f, leads to a pseudo-functor between pseudo-monoid structures, as in the picture. But in particular, we are interested in cases where X and B are Cartesian monoidal, or well, the monoidal structure is Cartesian, in which case we call P a Cartesian monoidal fibration. And moreover, we would like F to lift groups to groups. So we had this result. Let P be a Cartesian monoidal fibration, F it's associated pseudo-functor. Then F is groupal, which means that F leads to a pseudo-functor between the corresponding group structures, pseudo-group structures, if and only if these two conditions hold. That is, for each X in X such that its image via P is a group, then the terminal arrow of X is of Cartesian, and for the same kind of object, the diagonal arrow is also of Cartesian. And in particular, this holds when the fibers of P are groupoids, because in that case, all arrows are of Cartesian. So those conditions hold for free, and F is groupal. And that's precisely what we want. And there's even a more interesting result, which is the following. If B is an additive category, and P is a Cartesian monoidal fibration, and F is its associated pseudo-functor, then this pseudo-functor factors through the two categories of symmetry to groups, if and only if the fibers of P are groupoids. So it suffices to have groupoids in the fibers to have a pseudo-functor of this kind. And this is where we got finally. I don't know how much time I have.
Well, officially,
I'm out.
Well, no, because you can steal some time from the questions.
Okay. Well,
not
maybe
too much time.
Okay. Maybe I go here, which is the main point. If we start with the fiber-wise of fibration satisfying additional property that I don't want to now explain, there's a way to factor this fiber-wise of fibration to get groupoidal fibers and to get a fiber-wise of fibration still with the same properties. And so we end up in a situation like the one of this theorem below. And in particular, this applies to this triangle. So we have an intrinsic way of defining cohomology to groups. Well, I don't want to take too much time. Okay, thank you.
Thank you very much, Alan. And so we have plenty of time for questions. Anybody can unmute it and ask. Comments?
Enrico,
please.
Thank you, Alan. At a moment during your talk, you said that in this way we get an intrinsic definition of cohomology groups in a semi-abelian context, and even more in general. Can you say something about this more general?
Yes. I suspect it is not the level of generality you would like, probably. But the point is that it suffices to have a triangle that satisfies the property we need. So it has to be a fiberwise opfibration. Let me go here. Okay, can you see my slides?
Yes.
Okay, we need this. A fiberwise opfibration where the fibers of P0 and U have finite products and change of base preserve them, and the restriction of P to any fiber is an opfibration which preserves finite products. So a priori, there are plenty of situations of this kind. In particular, you can take Hochschild cohomology for associative algebras, which does not fit in the semi-abelian framework, but it fits here. So that's an example. But I remember your question in Brussels. You asked me if we could do something like this in the case of two groups, of symmetric categorical groups. And well, I don't have an answer for that, but there is a point which I think is important. We defined groupal pseudofunctors, which are pseudofunctors from a category to cat, from a Cartesian monoidal category to cat, that send groups to groups, to pseudo groups. So groups to symmetric categorical groups. In that situation, you don't start from a Cartesian monoidal category. It's something more general. So you would need a more general definition than the one of groupal pseudofunctor. I think that's a sensible point. It should be, say, a two-dimensional analog of the notion of off-monoidal functor. It should be a notion of off-monoidal pseudofunctor. I'm not sure this exists. This even exists. So that is a sensible point, I think.
Okay, thank you.
You're welcome.
Thank you, Enrico, and thank you, Alan, for your answer. Other questions or comments? Or suggestions? We also like suggestions of examples.
There is a question in the chat. Maybe Alan.
Can you explain what is an opfibration?
Okay, is the dual notion of that of fibration. Instead of having Cartesian lifting, well, I should write maybe somewhere. Let me try. Can you see this sort of board?
Yes, we can.
Okay. So say a functor f from x to b is an opfibration if for each arrow beta downstairs and each object x upstairs over b of the domain of beta, there exists a unique lifting of this. So an arrow's image is beta, and such that for any other arrow whose image factors through beta, there is a unique factorization. So here, this is not unique. Okay. Okay, maybe. Is it okay?
Thank you. Yes. So the following question would be, why call it opfibration and not cofibration? But this is too difficult to... Okay, there is a long story about this, but we won't tell it now. About terminology. So, any other question? If not, and I think there are not, let's thank Alan again and all the other speakers that joined us in this first episode of our running seminars. And you will find information about the next episodes on the website. And I would like also to thank all the people that participate and joined us in this seminar. Thank you very much. And well, now the seminar is closed, so you can also remain and have a coffee or whatever you like. And thank you again. And now gossip, right?
I will leave the last sentence in the recording and put it on.
Yeah, we stop the recording. We really start before gossiping. Otherwise, it's
exactly. I stopped my recording and yeah.
I don't find my stopping recording. Here it is. No, here.